Hello everyone. So today we are going to discuss a programmable logic array design problem. Before solving the problem, let us first understand the basic concept of programmable logic devices, commonly called PLDs, and then move on to the PLA structure. Okay. So first, what is PLD? So the expansion for this PLD is programmable logic device. Okay. So this is nothing but a digital device in which logic function is not fixed. Okay. So during your manufacturing process. Okay. Instead, the user can program the device to implement the required Boolean logic functions. So these PLDs are widely used to reduce hardware complexity. Okay. Then this is widely used to implement your complex logic in your compact form. Okay, and it can also used to modify the logic functions without changing the hardware components. Okay, so some of the PLDs are PLA, PAL, CPLD, and FPGA. Okay, so PLA is nothing but programmable logic array, and PAL is nothing but programmable array logic. Okay, and CPLDs is nothing but complex programmable logic device. And FPGA is nothing but field programmable gate array. Okay. So in this video, our focus will be on the programmable logic array. Okay. So first we'll discuss what is PLA. PLA consists of two parts. That is, first one is programmable and plain. Okay. And another one is programmable or plain. So this means we can program which inputs are connected to your AND plane, and we can program which product terms are connected to your OR gate. Because both planes are programmable, PLA is highly flexible. Okay, it can also share the product terms among multiple output, which make it very efficient when multiple Boolean functions have common logic. So, therefore, the PLA is ideal when hardware optimization is required. So now let us move to the given problem. So this is our problem. Develop the list of minterms for F1 and F2. Organize the common product terms and form the required three product terms to output PLA structure. So that means we need to form three product term and two output PLA structure. So they have given our functions. So F1 is nothing but summation M of 357 and F2 is nothing but summation M of 457. So here they have given the minterms for the two functions, that is nothing but our two outputs, right? So first what we have to do is, our objective is to identify the common product terms. Okay, so then we have to implement both functions using three product terms and two output PLA. So here is our first step, identify the number of variables, right? So here we have 7, right? The highest minterm number in the given function is 7. So that means we require 3 input variable. So we consider or we assume it as A, B, C. Okay, it's up to you. You can assume it as X, Y, Z, right? So next what we have to do is we have to construct this minterm table. Now we are going to construct the table with these inputs A, B, C and the output F1 and F2. For F1, the output is 1 at minterms 3, 5 and 7. So I have substituted 1 here, here and here. So these inputs are same as usual. We have 8 possible combinations. So 0, 1, 2, 3, 4, 5, 6, 7. So the binary representation for these numbers. So now corresponding to 3, 5 and 7, we have substituted 1 as the output for F1. And same for your F2, 1, the output will be 1 for 4, 5 and 7. So here 4, 5 and 7, we have substituted the output as 1. right? So this is your minterm table. So with the help of this minterm table, what we have to do is we have to simplify this one using K-map. Okay, so we all are aware of K-map. So now we are going to use this K-map. So this is a three variable K-map. So here comes A, B, C, and here 0, 1. 0, 0, 0, 1, 1, 1, 1, 0. One bit change here, right? So this is nothing but 0, 1, and here 2, 3, and 4, 5, 6, 7, right? So now we have to substitute this one here output for F1. So here 0, and next we have to substitute this part here 0, and next we have to substitute 0 here and 1 here. Next we have 0, 1, and again we have 1 here. So that means 7 is 1 and 0 here, right? So now we have to map these ones. So the highest number of ones here is 2, and here also 2. That means we have to pair the 2. Right? So we have two pairs, okay, first pair and second pair. So now we have to take the Boolean function for these two pairs. So the first part I will take means 0 and 1, it get cancelled. The corresponding BC value is BC plus. Now we have to consider the second part. So now the corresponding A is 1. So A, and here 0 and 1 for B is cancelled. And C 1 1 is there. So AC. So this is my Boolean function for my function F1. Next for F2. Okay. So we have to simplify the help of K-map. So again same ABC here. 0, 1. So 0, 0, 0, 1, 1, 1, 1, 0. So we'll fix here. So 0, 0, 0, 0. Next 1, 1, 1, 0. So again we have to pair these ones like this. Okay. So this is my first pair and this is my second pair. So first pair we will have here 1. So that means A, and corresponding BC terms becomes B bar. Right? So again, if we take the second pair, so the corresponding A will be A, and here BC term, B will get cancelled and C will be 1, so C. Okay, so this is my F2 term. So F2 is nothing but A, B bar plus A, C. Right? So this is my second step. Okay, so we have to simplify this one with the help of K-map. Okay, so now we'll get, after mapping that once and grouping them, we obtain the simplified expression for F1 and F2, right? So next step, okay, so what we have to do is we have to identify the common product terms. Okay, so we have F1 and F2 here. The common product term in F1 and F2, okay, in both F1 and F2 is AC, and here also AC, right? So apart from that, what are the other product terms we have? BC, A, B bar. So we have to substitute here. Okay. So this is our PLA programming table. So here we have to substitute our product term. It's nothing but the first product term here is BC, and next we have A, B bar, and next we have A, C, right? So next, A, B, C input are there and output F1 and F2. What we have to do is, so here we don't have A part, right? So that means here hyphen, and here we have A, B part, and here we have C part, so 1, 1. So here what we have to do is whether this BC product term is in our F1 or not. Yes, it's included in our F1. So here comes your 1. And whether this BC included in our F2 part? No. So that means here hyphen. Okay. So again, the same procedure repeats for other two product terms. So A, B bar. So A is here, so 1. And B is also here. It's nothing but B bar. So here 0. And C is not here, so hyphen. And this product term is in the F1 part? No. So that means here hyphen, and F2, yes. So that means 1. And AC is nothing but A is 1 and B is not here and C is 1, right? So now this is included in our first F1 also and in F2 also. So 1, 1, right? So now what we have to do is with the help of this PLA programming table, okay? So we have to substitute that product term in our logic diagram, okay? So the next one is our PLA structure. So the PLA structure look like this. So we have A, B, C, and we have to take A bar, B bar, C bar with the help of this NOT gate, right? So here we have three product terms. So that means we have to substitute three and plane, okay? And we have two outputs here. So that means we have to give two OR gates here, okay? OR plane here, okay? So in AND plane, the input A, B, C are used to generate three product terms, okay? In OR plane, the product terms A, C, B, C, A, B bar are connected to F1 and F2. Okay, so thus we have successfully designed a three product term to output PLA, right? So in this problem, we learned how to convert minterm into Boolean function and how to identify common product terms and how multiple outputs can be efficiently implemented using PLA. This example clearly demonstrates why PLA is preferred when multiple Boolean functions share common logic, right? So thank you so much.